Hello there, and welcome to this gentle corner of the cosmos, where the universe's most explosive secrets get wrapped in wonder and curiosity takes a thoughtful stroll through the extraordinary. Tonight's peaceful journey is all about something that sounds like pure science fiction but exists all around us. Antimatter, the universe's most dangerous substance, and perhaps its most beautiful paradox. Right now, as you're watching, the cosmic rays are creating tiny specks of antimatter high above your head. Yet this seemingly invisible substance holds enough power to make our most powerful rockets look like gentle candles, and it disappears the moment it touches anything made of ordinary matter, which, rather inconveniently, includes everything we know and love. But before we unravel the elegant mystery of antimatter, I'd love to know, where in the world are you watching from, and what time is it for you right now? Fitting, isn't it? Here we are, scattered across time zones, each of us made of ordinary matter, contemplating its perfect opposite. If you find this voyage soothing, intriguing, or just a nice way to unwind after a long day, I'd be ever so grateful if you gave the video a like, and maybe subscribed. It helps this little corner of calm reach others who might need a peaceful pause with the universe's most fascinating puzzles. Now, I do hope this isn't so captivating that it keeps you awake pondering the nature of existence, but if it does, well, at least you'll drift off knowing something remarkable about the invisible dance between matter and its mirror image. So settle in, slow your thoughts, and let's begin. Because somewhere between the tiniest particles and the vastest cosmic explosions, between creation and annihilation, lies the elegant story of antimatter. Have you ever held something ordinary in your hands? A coin, a pebble, a leaf, and wondered what it's really made of? Not the obvious answer. Not copper, or rock, or chlorophyll, but the deepest answer. What sits at the very bottom of everything, like the final Russian doll inside all the others? This question has been whispering to humanity for thousands of years, patient as starlight. It's the question that made ancient philosophers pace under olive trees, that kept alchemists awake by candlelight, that still makes children stare at their own hands with sudden wonder. What is the smallest thing? What is the piece that can't be divided anymore? The Greeks had a word for it, atomos, meaning uncuttable. They imagined these tiny invisible particles dancing through empty space, combining and separating like cosmic Lego blocks. They had no microscopes, no laboratories, no way to prove their wild idea. They simply looked at the world and thought, this complexity, this endless variety of things, must come from something simpler. And they were right, though they could never have imagined how right they were. The atom isn't just the smallest piece of matter, it's the strangest. It's mostly empty space, yet it holds together everything we touch. It's governed by rules that defy common sense, yet it creates the sensible world we inhabit. It's smaller than anything we can truly comprehend, yet it contains energy that can power cities or level them. When you breathe, trillions of atoms flow through your lungs, atoms that were once inside dinosaurs, inside ancient seas, inside the hearts of stars. When you think, atoms arrange themselves in patterns that somehow become consciousness, memory, love. The very act of wondering about atoms is atoms wondering about themselves. This is why the question never left us. Because atoms aren't just what we're made of, they're what we are. Every emotion, every thought, every moment of beauty or terror is ultimately a story about how atoms dance together in the dark. And that brings us to the beginning of their story. To the dreamers who first dared to imagine the invisible. Picture yourself in ancient Greece, around 400 BCE, sitting by the Mediterranean as the sun sets over water that stretches to the horizon. A philosopher named Democritus is walking along the shore, picking up handful after handful of sand. He lets the grains fall through his fingers, watching them scatter in the wind. What if, he wonders aloud, I could keep dividing these grains in half, and in half again, and again? Would I eventually reach something so small it couldn't be divided anymore? This wasn't just idle curiosity. This was revolutionary thinking. Most people believed that matter was continuous, like honey, or water, something you could divide forever. But Democritus imagined something different, a world made of tiny, indivisible particles moving through empty space. He called them atoms, from the Greek word meaning uncuttable. His teacher, Leucippus, had planted the seed of this idea, but Democritus nurtured it into something beautiful. He pictured atoms as tiny, solid shapes, some round, some angular, some with hooks that let them link together. Different combinations of atoms, he thought, made different things. Sweet things had round, smooth atoms, while bitter things had sharp, jagged ones. It was poetry disguised as physics, but it contained a truth that wouldn't be proven for over 2,000 years. Democritus imagined that atoms were eternal. They couldn't be created or destroyed, only rearranged. Nothing exists except atoms and empty space, he declared. Everything else is opinion. This was breathtaking in its simplicity and audacity. He was saying that all the complexity of the world, every sunset, every flower, every human emotion, was just atoms dancing in different patterns. But then came Aristotle, the great systematizer of knowledge, who disagreed. Aristotle believed in 4 elements: earth, air, fire, and water. He thought empty space was impossible. Nature, he said, abhors a vacuum. His influence was so powerful that Democritus's atomic theory was almost forgotten for nearly 2 millennia. It wasn't until the early 1800s that a quiet English schoolteacher named John Dalton rescued the atomic idea from history's dustbin. Dalton wasn't a philosopher dreaming by the sea. He was a practical man who noticed patterns in the way chemicals combined. He observed that elements always combined in simple, whole number ratios, as if they were made of discrete particles. Water, he noticed, was always made of hydrogen and oxygen in a ratio of 2:1. Salt was always sodium and chlorine in a 1:1 ratio. This suggested that matter came in uniform, indivisible units, atoms, just as Democritus had imagined. Dalton's atomic theory was more precise than the Greek version. He proposed that all atoms of the same element were identical, that atoms of different elements had different weights, and that chemical reactions were simply atoms rearranging themselves into new patterns. He even calculated relative atomic weights, though his numbers were rough approximations. The ancient dream was becoming scientific reality. From Democritus's philosophical insight to Dalton's careful observations, the idea of atoms had survived, evolved, and was finally ready to be tested. But how do you test something you can't see? How do you prove the existence of particles too small for any eye to detect? That challenge would define the next century of science, as researchers developed increasingly clever ways to study the invisible foundation of everything. Imagine trying to convince someone that the air around them is made of tiny invisible balls bouncing around like microscopic ping-pong balls. This was the challenge facing scientists in the 1800s, as they tried to prove that atoms were real, not just a useful idea. The breakthrough came from an unexpected place: the study of gases. In laboratories across Europe, researchers were heating gases, cooling them, compressing them, and measuring how they behaved. What they discovered was a mathematical poetry hidden in the chaos. Robert Boyle, an Irish natural philosopher, noticed something remarkable. When you squeeze a gas into half the space, its pressure doubles. When you squeeze it into a third of the space, pressure tripled. It was as if the gas were made of particles that pushed back harder when crowded together, like commuters on a subway platform during rush hour. Jacques Charles, a French physicist famous for his hot air balloon flights, discovered that gases expand when heated in a perfectly predictable way. Cool them down, and they contract, just as predictably. Again, this made sense if gases were made of tiny particles moving faster when hot, slower when cold. But the most elegant discovery came from Amedeo Avogadro, an Italian physicist who realized something profound. Equal volumes of different gases at the same temperature and pressure contain the same number of particles. This meant that a liter of hydrogen contains the same number of atoms as a liter of oxygen, even though oxygen atoms are 16 times heavier. This was like discovering that every parking lot in the world, regardless of size, holds exactly the same number of cars. It suggested that atoms weren't just real, they were countable, measurable, and followed rules as precise as clockwork. The Scottish botanist Robert Brown added another piece to the puzzle in 1827. While studying pollen grains under a microscope, he noticed something strange. Tiny particles suspended in water jiggled around randomly, as if they were being pushed by invisible hands. This Brownian motion was exactly what you'd expect if water were made of atoms constantly colliding with the pollen grains. It was like watching a crowd of people you couldn't see, but knowing they were there because you could watch someone being jostled by them. By the late 1800s, the evidence was overwhelming. The kinetic theory of gases painted a picture of atoms as tiny, hard spheres in constant motion. Temperature was just the average energy of this motion. Pressure was the result of countless atomic collisions with container walls. Even phenomena like diffusion, how perfume spreads through a room, made perfect sense if air were made of moving particles. Ludwig Boltzmann, an Austrian physicist, developed the mathematical framework that described this atomic ballet. His equations showed how the behavior of trillions of invisible particles could create the predictable properties of gases, liquids, and solids. He calculated that a single gram of water contains roughly 33 billion trillion atoms, a number so large it's almost meaningless to our everyday minds. But Boltzmann's work was controversial. Many prominent scientists still doubted that atoms were real. They saw atomic theory as a useful fiction, a mathematical tool that worked but didn't necessarily describe reality. The debate grew so heated that some physicists dismissed atoms as mere mental constructs. This skepticism would persist until the early 1900s, when new discoveries finally made atoms impossible to ignore. The invisible universe was about to become visible, not through better microscopes, but through increasingly ingenious experiments that revealed the atomic world's most shocking secrets. Before anyone could see an atom, they had to imagine it. And the images that danced in scientists' minds were as varied as the dreams of children, some beautiful, some strange, all reaching toward a truth that seemed just beyond their grasp. In the late 1800s, if you asked a physicist what an atom looked like, you might get a dozen different answers. Lord Kelvin, the brilliant Scottish physicist, imagined atoms as tiny vortices spinning in an invisible fluid, like miniature whirlpools in the fabric of space itself. He spent years developing this theory, convinced that atoms were essentially knots in the ether, that mysterious substance that was thought to fill all of space. J.J. Thomson, the discoverer of the electron, pictured atoms differently. After finding that atoms contained negatively charged particles, he imagined them as plum puddings, spheres of positive charge with electrons embedded in them like raisins in a cake. It was a cozy, Victorian image. Atoms as tiny Christmas puddings, each ingredient playing its part in the cosmic feast. Ernest Rutherford, Thomson's former student, had an even more radical vision. Through his famous gold foil experiment, he discovered that atoms were mostly empty space, with a tiny dense nucleus at the center. He imagined atoms like miniature solar systems, with electrons orbiting the nucleus like planets around the sun. But each of these mental pictures created new puzzles. If atoms were like solar systems, why didn't the electrons spiral into the nucleus? According to classical physics, orbiting electrons should constantly radiate energy and crash into the center within a fraction of a second. The entire universe should have collapsed before it even got started. Niels Bohr, a young Danish physicist, proposed a solution that was both elegant and bizarre. He suggested that electrons could only exist in specific orbits, like cars that could only drive in certain lanes. When electrons jumped from one orbit to another, they would emit or absorb specific amounts of energy, quanta, explaining the distinctive colors of light that different elements produced when heated. This was the beginning of quantum mechanics, though nobody called it that yet. Bohr's model worked mathematically, but it defied common sense. Why could electrons only exist in certain orbits? What determined these mysterious energy levels? It was like discovering that you could only walk at certain speeds, never faster than 3 miles per hour, never slower than 2 miles per hour, with no speed allowed in between. Arnold Sommerfeld refined Bohr's model by adding elliptical orbits and accounting for relativistic effect. His atoms looked like complex astronomical systems, with electrons tracing elaborate paths around the nucleus. The calculations were beautiful and precise, but the underlying assumptions grew increasingly strange. As the 1920s approached, the atomic imagination was reaching its limits. Scientists had created increasingly sophisticated models, but each solution created new problems. The atom was revealing itself to be far stranger than anyone had imagined. Not just small, but fundamentally different from anything in the visible world. Louis de Broglie, a French physicist, suggested something revolutionary. What if electrons weren't particles at all, but waves? Just as light could behave like both a wave and a particle, maybe matter itself had a wave-like nature. This idea seemed absurd. How could something solid be a wave? But it opened the door to a new way of thinking about atoms. Werner Heisenberg took this thinking even further, developing a mathematical framework that didn't try to visualize atoms at all. Instead of asking what does an atom look like, He asked, what can we measure about an atom? His uncertainty principle suggested that there were fundamental limits to how precisely we could know an atom's properties, that the very act of observation changed what we were observing. Erwin Schrödinger created perhaps the most beautiful mathematical description of atoms, treating electrons as probability waves that surrounded the nucleus like clouds of possibility. In his equations, electrons didn't have definite positions. They existed in a superposition of all possible states, until measured. These weren't just different theories. They were different ways of imagining reality itself. The atom was forcing scientists to abandon their comfortable visual models and embrace mathematical descriptions that challenged the very notion of what it meant for something to exist. And that brings us to the moment when imagination met reality, when the tools finally became powerful enough to glimpse the atomic world directly. How do you see something that's smaller than light itself? This question haunted scientists for over a century, because atoms are so tiny that ordinary light waves simply wash over them like ocean waves passing over a pebble. To see an atom, you need to be more clever than your eyes. The first breakthrough came from studying what atoms left behind, their fingerprints rather than their faces. In 1897, J.J. Thomson was experimenting with mysterious cathode rays that glowed inside glass tubes when electricity passed through them. By bending these rays with magnets and measuring their deflection, he discovered that they were made of particles much smaller than atoms themselves. He had found the electron, the first subatomic particle. It was like discovering that houses were made of bricks by catching the chips that fell off when you hit the wall with a hammer. Thomson couldn't see electrons directly, but he could measure their charge and mass, proving that atoms weren't indivisible after all. Ernest Rutherford took this detective work further in 1909. He aimed a beam of alpha particles, helium nuclei, at a thin sheet of gold foil, expecting them to pass through like bullets through tissue paper. Instead, most particles sailed through undeflected, but a few bounced back as if they had hit something incredibly dense and small. "It was quite the most incredible event that has ever happened to me in my life," Rutherford later said. "It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." This experiment revealed that atoms were mostly empty space with an incredibly tiny dense nucleus at the center. Rutherford had discovered the atomic nucleus by watching what happened when he threw things at atoms, like mapping a dark room by listening to what your thrown tennis balls hit. But the most beautiful window into the atomic world came from light itself. When elements are heated, they don't glow white like a hot coal. They emit specific colors, like atomic signatures. Hydrogen glows with a distinctive red, blue and purple pattern. Sodium creates a bright orange. Each element has its own unique spectrum, as individual as a fingerprint. This was spectroscopy, the art of reading atomic light. Scientists realized that these colors were messages from the atomic world, telling them about the energy levels of electrons. When electrons jumped between orbits, they absorbed or emitted photons of specific energies, creating the lines in the spectrum. Gustav Kirchhoff and Robert Bunsen, yes, the Bunsen burner, Bunsen, used this technique to discover new elements. They would analyze the light from heated samples and find spectral lines that didn't match any known element. Cesium and rubidium were discovered this way, found in the light, before they were found in the laboratory. The cloud chamber, invented by C.T.R. Wilson in 1911, provided another way to see atomic events. This device created a supersaturated vapor that would condense into droplets along the paths of charged particles. Suddenly, scientists could see the tracks left by individual atoms and subatomic particles, like contrails in the sky showing where invisible planes had passed. X-ray crystallography, developed by William and Lawrence Bragg, revealed the arrangement of atoms in crystals. By bouncing X-rays off crystal surfaces and analyzing the resulting patterns, they could map the positions of atoms with remarkable precision. It was like using shadows to deduce the shape of the objects casting them. Marie and Pierre Curie's work with radioactivity provided perhaps the most dramatic proof of atomic reality. They discovered that some atoms spontaneously emit particles and energy, transforming into different elements in the process. Here was direct evidence that atoms were not eternal and unchanging. They could be born, they could die, and they could transform into something else entirely. The Geiger counter, developed by Hans Geiger and Ernest Rutherford, could detect individual radioactive decays. Each click represented a single atom transforming itself, announcing its change with a burst of energy. For the first time, scientists could count atoms one by one. By the 1920s, The atomic world was no longer completely invisible. Scientists had learned to read its signals, to interpret its messages, to glimpse its structure through increasingly sophisticated tools. They still couldn't see atoms directly, but they could see their effects, their emissions, their interactions. The unseeable was becoming visible, one clever experiment at a time. And what these experiments revealed was more shocking than anyone had imagined. A world where the very foundations of reality were far stranger than the most imaginative dreams. Take a moment to touch something solid. Your desk, a wall, your own hand. It feels reassuringly real, doesn't it? Dense, substantial, unmistakably there. Now prepare to have your mind quietly blown. What you're touching is almost entirely empty space. This is perhaps the most startling discovery in the history of science. If an atom were the size of a football stadium, the nucleus would be a marble sitting on the 50-yard line. The electrons would be smaller than gnats, buzzing around somewhere in the parking lot. Everything else, the vast majority of the atom, is nothing but empty space. Ernest Rutherford discovered this shocking truth in 1909 through his famous gold foil experiment. He expected alpha particles to pass through the thin gold sheet with only minor deflections, like bullets passing through fog. Instead, while most particles sailed through unimpeded, a few bounced back dramatically. The only explanation was that atoms contained something incredibly small and incredibly dense. The nucleus. The numbers are staggering. If you could somehow squeeze all the empty space out of your body, you would be smaller than a grain of sand. If you could do this to all the people on Earth, we would fit comfortably inside a sugar cube. The entire human race, compressed to nuclear density, would be about the size of a small marble. This emptiness isn't just a quirk of atomic structure. It's fundamental to how matter behaves. The solid resistance you feel when you push against a wall isn't atoms bumping into each other like billiard balls. Instead, it's the electromagnetic force fields around atoms pushing back against each other, like trying to push together two magnets with the same poles. When you sit in a chair, you're not actually touching it in the way you imagine. The electrons in your body are repelling the electrons in the chair, creating an electromagnetic barrier that feels like solid contact. You're essentially hovering above the chair, held up by invisible force fields. The feeling of touch is an illusion created by electromagnetic repulsion. This explains why matter can seem so solid while being mostly empty space. The forces between atoms are incredibly strong. The electromagnetic force that keeps your hand from passing through a table is about 1036 times stronger than gravity. These invisible barriers are more impenetrable than any physical wall. But here's where it gets even stranger. The nucleus itself, despite being incredibly dense, is also mostly empty space. Protons and neutrons are made of smaller particles called quarks, and quarks are held together by the strong nuclear force. Most of the nucleus's mass doesn't come from the quarks themselves, but from the energy of the force field that binds them together. Einstein's famous equation E=mc² tells us that mass and energy are interchangeable. Much of what we experience as the solid, substantial mass of matter is actually the energy of force fields, electromagnetic fields, strong nuclear force fields, weak nuclear force fields. Matter is more like a symphony of energy than a collection of tiny building blocks. This emptiness has profound implications for how we understand reality. The solid world we experience is a kind of collective hallucination created by electromagnetic forces. The thingness of things is really a pattern of forces in mostly empty space, like a dance performed by invisible dancers. Quantum mechanics adds another layer of strangeness. Even the particles themselves don't have definite positions or properties until measured. An electron isn't a tiny ball orbiting the nucleus. It's a probability cloud, a fuzzy region where the electron might be found if you look for it. The atom is less like a miniature solar system and more like a ghost made of possibilities. This understanding changed everything. If atoms are mostly empty space, then everything, your coffee cup, your cat, your thoughts, is mostly empty space held together by force fields. The universe isn't made of stuff. It's made of patterns in the void, structures in the emptiness, something arising from nothing. And yet, from this almost nothingness emerges everything we know and love. The complexity of life, the beauty of art, the warmth of human connection. All of it dancing in the spaces between spaces. All of it arising from the mysterious architecture of mostly empty atoms. This brings us to the dense heart of the atom, the tiny nucleus that contains virtually all of its mass. Imagine compressing all the mass of a mountain into a space smaller than a pinhead. That's the kind of density we're talking about when we peer into the heart of the atom. The nucleus, a realm where the ordinary rules of size and space seem to break down completely. The nucleus is where atoms keep their identity. Strip away all the electrons from a hydrogen atom, and you still have hydrogen, just ionized hydrogen. But change the nucleus, and you have a completely different element. The nucleus is like an atom's birth certificate, determining whether it will be gold or lead, oxygen or carbon, uranium or helium. Ernest Rutherford first glimpsed the nucleus in 1911, but it took decades to understand what was actually inside this impossibly small, impossibly dense core. By the 1930s, scientists had identified the nuclear cast of characters, protons and neutrons, collectively known as nucleons, bound together by the strongest force in nature. Protons carry positive electrical charge, exactly equal and opposite to the negative charge of electrons. The number of protons in a nucleus determines the element. 1 proton means hydrogen, 6 protons means carbon, 79 protons means gold. It's that simple and that absolute. Change a single proton, and you transform one element into another. The ancient dream of alchemy, but achieved through nuclear physics rather than mystical practices. Neutrons, as their name suggests, are electrically neutral. They're slightly heavier than protons but incredibly similar in other ways. Discovered by James Chadwick in 1932, neutrons were the missing piece that explained why atomic masses weren't simply multiples of hydrogen's mass. A carbon-12 nucleus, for instance, contains 6 protons and 6 neutrons, giving it roughly 12 times the mass of a hydrogen nucleus. But here's where nuclear physics gets beautifully strange. The mass of a nucleus is less than the sum of its parts. If you could somehow separate all the protons and neutrons in a carbon nucleus and weigh them individually, they would be heavier than the intact nucleus. The missing mass, called the mass defect, has been converted into binding energy, the force that holds the nucleus together. This is Einstein's Ising C. in action. The strong nuclear force is so powerful that it literally converts some of the nucleon's mass into the energy needed to bind them together. It's like the nucleus pays a mass tax to stay assembled, with the collected mass becoming the glue that holds everything together. The strong nuclear force is remarkable in its property. It's incredibly powerful, about 100 times stronger than the electromagnetic force that binds electrons to atoms. But it's also incredibly short-ranged, operating only over distances comparable to the size of the nucleus itself. This is why atomic nuclei can exist at all, beyond the nucleus. The strong force essentially disappears, allowing electrons to orbit without being pulled into the core. The balance between the strong nuclear force and electromagnetic repulsion creates the delicate architecture of the nucleus. Protons want to repel each other because they carry like charges, but the strong force holds them together. Add too many protons, and electromagnetic repulsion wins. The nucleus becomes unstable and radioactive. This is why there are no stable elements beyond bismuth, 83 protons in nature. Neutrons play a crucial role in nuclear stability. They don't carry electrical charge, so they don't add to the electromagnetic repulsion, but they do contribute to the strong force binding. This is why heavier nuclei need more neutrons than protons to remain stable. Iron 56, with 26 protons and 30 neutrons, sits at the sweet spot of nuclear stability, the most tightly bound nucleus in nature. The nuclear landscape is populated by isotopes, atoms with the same number of protons, but different numbers of neutrons. Carbon-12 and carbon-14 are both carbon, but carbon-14 has 2 extra neutrons that make it radioactive. These isotopes are like nuclear siblings, similar in chemistry but different in nuclear behavior. Some nuclei are perfectly stable, content to exist unchanged for billions of years. Others are restless, constantly threatening to break apart or transform into something else. The half-life of unstable nuclei ranges from fractions of a second to billions of years, creating a nuclear clock that ticks at different rates for different isotopes. The nucleus also harbors incredible amounts of energy. The binding energy that holds nucleons together is millions of times greater than the energy binding electrons to atoms. This is why nuclear reactions release so much more energy than chemical reactions. You're tapping into the deepest energy reserves of matter itself. But the nucleus isn't just a passive repository of protons and neutrons. It has structure, behavior, and personality. Some nuclei are spherical, others are elongated or flattened. Some can be excited into higher energy states, like atomic versions of spinning tops. Some can even be split apart or fused together, releasing the tremendous energies that power stars and nuclear reactors. This brings us to the ghostly particles that dance around this dense nuclear core, electrons, the mysterious inhabitants of the atom's vast outer regions. If the nucleus is the atom's dense, concentrated heart, then electrons are its restless, ethereal soul. These particles are so light, so fast, so fundamentally strange, that they challenge our very notion of what it means to be a particle at all. An electron weighs about 1/8036th as much as a proton, making it a wisp of matter compared to the nuclear heavyweights. If a proton were a bowling ball, an electron would be lighter than a marble. And yet this tiny particle carries exactly the same amount of charge as a proton, just with opposite sign. It's like discovering that feathers and anvils can carry the same amount of electrical force. But here's where electrons become truly mysterious. They don't actually orbit the nucleus like planets around the sun, despite what every atomic diagram suggests. This classical picture, beautiful as it is fundamentally wrong. Electrons don't follow defined paths at all. Instead, they exist in probability clouds, regions where they might be found if you look for them. Quantum mechanics tells us that electrons are simultaneously everywhere and nowhere within their orbital regions. They exist in a superposition of all possible states until the moment of measurement collapses their wave function into a definite position. It's as if the electron is playing an eternal game of hide and seek, with the universe appearing only when someone looks for it. These probability clouds have beautiful, mathematical shapes. The simplest orbital, called 1 Cers, is a sphere centered on the nucleus. The 2p orbitals are dumbbell-shaped, with the electron more likely to be found in 2 lobes on opposite sides of the nucleus. Higher orbitals create increasingly complex patterns, cloverleafs, rings, and intricate 3-dimensional forms that look like abstract sculptures. Werner Heisenberg's uncertainty principle adds another layer of strangeness. The more precisely you know an electron's position, the less precisely you can know its momentum, and vice versa. This isn't just a limitation of our measuring instruments, it's a fundamental property of reality itself. Electrons don't have well-defined positions and momenta simultaneously. They exist in a quantum haze of probability. But electrons aren't just fuzzy clouds of possibility. They carry energy, and this energy comes in discrete packets called quanta. Electrons can only exist in specific energy levels, like someone who could only climb a ladder using certain rungs while being forbidden from stopping at the rungs in between. When electrons jump between these levels, they emit or absorb photons of light, with exact energies determined by the energy difference between levels. This is why different elements glow with characteristic colors when heated. Hydrogen atoms emit a specific red, blue, and purple pattern, because their electrons can only make certain quantum jumps. Neon creates that distinctive orange-red glow, because its electrons have their own unique set of available energy transitions. Every element has its own spectral signature, as distinct as a fingerprint. Electrons also have an intrinsic property called spin, though they're not actually spinning like tiny tops. Quantum spin is more like an internal compass that can point in one of 2 directions, up or down. This property becomes crucial when electrons pair up in orbitals, always with opposite spins, like cosmic dance partners, maintaining perfect balance. The Pauli exclusion principle, discovered by Wolfgang Pauli, states that no 2 electrons in an atom can have exactly the same set of quantum numbers. This is why electrons arrange themselves in shells around the nucleus, with each shell capable of holding only a certain number of electrons. The first shell holds 2 electrons, the second holds 8, the third holds 18, and so on. This electron arrangement determines everything about an atom's chemical behavior. Sodium, with 11 electrons, has 1 lonely electron in its outer shell, making it eager to give that electron away in chemical reactions. Chlorine, with 17 electrons, has 7 electrons in its outer shell, and desperately wants 1 more to complete the set. When sodium meets chlorine, the result is salt, a stable compound formed by the transfer of that single electron, but electrons aren't confined to individual atoms. In metals, some electrons become delocalized. forming an electron sea that can flow through the material. This is why metals conduct electricity and heat so well. The mobile electrons carry energy and charge throughout the structure. In superconductors, electrons can flow without any resistance at all, creating currents that can persist forever. Electrons can also tunnel through barriers that should be impossible to cross, appearing on the other side of energy barriers without ever having enough energy to go over them. This quantum tunneling is essential to many modern technologies, from the scanning tunneling microscope to the fusion reactions that power the sun. Perhaps most remarkably, electrons can become entangled with each other, creating quantum correlations that persist even when the particles are separated by vast distances. Einstein called this spooky action at a distance, but it's now recognized as one of the fundamental features of quantum mechanics. The electron is matter's most mysterious messenger, carrying information about energy, charge, and quantum states throughout the atomic world. Understanding their behavior leads us to the beautiful architecture of electron shells and the periodic patterns they create. Imagine atoms as cosmic apartment buildings, with electrons as the tenants who must follow very specific rules about where they can live. Some floors can hold only a few residents, others can accommodate more, and there are strict regulations about which apartments can be occupied when. This is the shell structure of atoms, and it's one of the most elegant organizational systems in the entire universe. The first shell, closest to the nucleus, is like a cozy studio apartment that can hold only 2 electrons. These electrons are in the 1s orbital, spherically shaped, and hugging close to the nuclear core. They're the most tightly bound electrons in the atom, content in their simple symmetric home. The second shell is more like a duplex, with room for up to 8 electrons. It consists of 1 2s orbital, another sphere but larger than the 1s, and 3 2p orbitals, those dumbbell-shaped probability clouds we met earlier. The 2s orbital can hold 2 electrons, while each 2p orbital can hold 2 electrons, for a total of 8 electrons in the second shell. The third shell is even more elaborate, capable of housing up to 18 electrons. It includes 3s, 3p and 3d orbitals, each with their own distinctive shapes and orientations. The d orbitals, in particular, have beautiful cloverleaf and ring-like patterns that create complex three-dimensional geometries around the nucleus. But here's where the shell game gets interesting. Electrons don't fill these shells randomly. They follow a strict hierarchy, always occupying the lowest available energy level first. This is called the Aufbau principle, German for building up, and it's like a cosmic building code that governs how atoms construct themselves. Within each shell, electrons follow additional rules. Hund's rule states that electrons prefer to occupy orbitals singly, before pairing up, like people who would rather have their own bedroom than share if possible. And when electrons do pair up in the same orbital, they must have opposite spins, nature's way of maintaining quantum balance. The Pauli exclusion principle ensures that no 2 electrons in an atom can have identical quantum properties. This creates the shell structure we observe, with electrons stacking up in orderly layers like architectural floors, each with its own capacity and characteristics. This electron architecture determines everything about an atom's personality. Atoms with completely filled outer shells, like helium, neon and argon, are supremely stable and chemically inert. They're the introverts of the atomic world, content in their completeness and reluctant to interact with other atoms. But atoms with partially filled outer shells are reactive, eager to achieve the stability of a complete shell. Sodium, with 1 electron in its outermost shell, readily gives up that electron to achieve the stable configuration of neon. Fluorine, with 7 electrons in its outer shell, aggressively seeks 1 more electron to complete its set. The number of electrons in an atom's outermost shell determines its chemical properties. Elements with the same number of outer electrons behave similarly, creating families of related elements. Lithium, sodium, and potassium all have 1 outer electron and show similar chemical behavior. Fluorine, chlorine, and bromine all have 7 outer electrons and form a family of reactive halogens. This shell structure also explains why atoms have the sizes they do. You might expect that atoms would simply get bigger as you add more electrons, but the reality is more complex. As the nuclear charge increases, it pulls more strongly on the electrons, partially offsetting the size increase from additional shells. This creates the subtle size variations we observe across the periodic table. The shell model also explains atomic spectra, those beautiful fingerprints of light that each element produces. When electrons jump between shells, They emit or absorb photons with energies exactly equal to the energy difference between levels. The shell structure acts like a cosmic piano, with each possible electron transition corresponding to a specific musical note of light. But the shell game has deeper implications. The arrangement of electrons in shells creates the fundamental forces that bind atoms together into molecules. When atoms approach each other, their electron shells can overlap, share electrons, or transfer electrons between atoms. This is the basis of all chemical bonding, the invisible handshakes that create everything from water molecules to DNA. The shell structure also explains why some atoms are magnetic. Unpaired electrons act like tiny magnets, and atoms with unpaired electrons in their outer shells can be attracted to magnetic fields. Iron, with its partially filled D shell, has unpaired electrons that make it ferromagnetic. This is why iron nails are attracted to magnets, and why Earth's magnetic field exists. It's ultimately a consequence of electron shell structure in iron atoms deep within our planet's core. And that brings us to the forces that hold all this atomic architecture together, the invisible powers that prevent atoms from flying apart or collapsing into themselves. Step back for a moment and consider the miracle of your existence. You are made of atoms, but atoms are made of charged particles that should, by all rights, either fly apart or crash together. Protons in the nucleus repel each other with tremendous force. Electrons should spiral into the nucleus and disappear. And yet here you are, stable and solid, held together by invisible forces that maintain the delicate balance of matter itself. 4 fundamental forces govern the universe, and 3 of them operate within the atom. These forces are the cosmic glue that prevents everything from dissolving into chaos or collapsing into oblivion. The strong nuclear force is the most powerful force in nature, but also the most mysterious. It operates only over distances comparable to the size of atomic nuclei, about 10 to 15 meters. Within this tiny realm, it's about 100 times stronger than the electromagnetic force, which is why it can hold positively charged protons together despite their electrical repulsion. The strong force doesn't care about electrical charge. It binds protons to protons, neutrons to neutrons, and protons to neutrons with equal enthusiasm. It's like a cosmic welding torch that operates only at the subatomic level, creating bonds so strong that breaking them releases the energy that powers the sun and the stars. But the strong force has a peculiar property. It gets stronger as particles move apart, like a rubber band that becomes harder to stretch. Try to pull 2 protons apart, and the strong force fights back with increasing intensity. This is why you can't isolate individual quarks, the particles that make up protons and neutrons. Pull hard enough, and you'll create new particles rather than separate existing ones. The electromagnetic force is the second strongest force in the atom, and it's responsible for almost everything we directly experience. It binds electrons to nuclei, creating stable atoms. It causes like charges to repel, and opposite charges to attract. It's the force you feel when you push against a wall, the force that creates the colors of light, the force that powers your electronic devices. This force operates over infinite distances, though it weakens with the square of the distance. It's carried by photons, particles of light, that zip back and forth between charged particles, creating the push and pull of electromagnetic. Every time you see light, you're witnessing the electromagnetic force in action. The electromagnetic force is also responsible for the Pauli exclusion principle, which prevents electrons from occupying the same quantum state. This exclusion creates the shell structure of atoms and determines their chemical properties. In a sense, the electromagnetic force is the architect of chemistry, determining how atoms can combine to form molecules. The weak nuclear force is the strange cousin of the nuclear family. It's much weaker than the strong force and operates over even shorter distances. Its main job is to oversee certain types of radioactive decay, particularly beta decay, where neutrons transform into protons or vice versa. The weak force is mediated by particles called W and Z bosons, which are much heavier than photons. This is why the weak force is so short-ranged. Its messenger particles are too heavy to travel far. It's like trying to send messages using bowling balls instead of letters. Despite its weakness, the weak force plays a crucial role in the universe. It's responsible for the nuclear reactions that power the sun, allowing hydrogen to fuse into helium and release the energy that sustains life on Earth. Without the weak force, the sun would be a cold, dark ball of hydrogen, and we wouldn't exist. The fourth fundamental force, gravity, is negligible within individual atoms. It's by far the weakest of the four forces, about 1039 times weaker than the strong force. Within an atom, gravity is like a whisper in a hurricane, completely overwhelmed by the other forces. But gravity has a special property. It's always attractive, and it operates over infinite distances. While the other forces can be positive or negative, attractive or repulsive, gravity only pulls. This means that, even though it's incredibly weak, it can accumulate over vast distances and enormous masses, eventually dominating the behavior of stars, planets, and galaxies. The interplay between these forces creates the stable structure of matter. The strong force binds nuclei together. The electromagnetic force keeps electrons in their shells while preventing them from falling into the nucleus. The weak force allows certain nuclear transformations that are essential for stellar evolution. And gravity, though negligible in individual atoms, provides the cosmic stage on which atomic drama unfolds. These forces also determine the fundamental constants of nature, the speed of light, the strength of electrical charge, the mass of fundamental particles. If any of these constants were slightly different, atoms, as we know them, couldn't exist. The universe would be either a soup of unbound particles or a collection of collapsed, ultra-dense nuggets of matter. The balance is so precise that physicists speak of the fine-tuning of the universe. The forces are perfectly calibrated to allow complex structures like atoms, molecules, and living beings to exist. Change any force by even a small percentage, and the universe would be radically different, and probably lifeless. This brings us to one of the deepest mysteries in physics. Why don't atoms collapse? What prevents the electromagnetic attraction between electrons and nuclei from overwhelming the kinetic energy of the electrons? Here's a puzzle that should keep you awake at night. According to classical physics, atoms shouldn't exist. Electrons orbiting a nucleus should radiate energy continuously, like a radio antenna broadcasting into space. As they lose energy, they should spiral inward, crashing into the nucleus in less than a billionth of a second. The universe should have collapsed into a dense soup of neutrons before the first star ever formed. Yet here we are, made of stable atoms that have existed for billions of years. What prevents this atomic apocalypse? The answer lies in the strange rules of quantum mechanics, which save the universe from its own instability. At the atomic level, the familiar laws of physics give way to something far more mysterious and beautiful. The first hint came from Max Planck in 1900, when he was trying to explain why hot objects glow the way they do. He found that energy comes in discrete packets, quanta rather than continuous streams. Energy, he discovered, is lumpy at the smallest scales, like matter that can only be sold by the pound, rather than by fractional ounces. Niels Bohr applied this insight to atoms in 1913, proposing that electrons can only exist in specific orbits with definite energies. These allowed orbits are like rungs on a ladder. An electron can stand on any rung, but never between rungs. When an electron jumps from one rung to another, it emits or absorbs a photon with energy exactly equal to the difference between energy levels. This explained why atoms emit light at specific wavelengths rather than a continuous spectrum. Each element has its own ladder of energy levels, creating its own unique set of possible quantum jumps, and its own spectral signature. But Bohr's model, while successful at explaining hydrogen spectrum, couldn't handle more complex atoms. The real breakthrough came with the development of wave mechanics by Louis de Broglie, Erwin Schrödinger, and Werner Heisenberg in the 1920s. De Broglie proposed that electrons aren't particles at all, they're waves. Just as light can behave like both a wave and a particle, matter has wave-like properties at the atomic scale. An electron orbiting a nucleus is like a standing wave wrapped around the atom, creating patterns of constructive and destructive interference. Schrödinger developed a mathematical equation that describes these matter waves. His wave function doesn't tell you where an electron is. It tells you where it might be found if you look for it. The electron exists in a superposition of all possible states, until the moment of measurement collapses it into a definite position. This wave nature of electrons is what prevents atomic collapse. Just as you can't fit half a wavelength of a musical note into a guitar string, you can't fit arbitrary electron waves into an atom. Only certain wavelengths corresponding to specific energy levels can exist as stable standing waves around the nucleus. The Heisenberg uncertainty principle adds another layer of protection. The more precisely you try to localize an electron, confine it to a smaller space, the more uncertain its momentum becomes. If you tried to squeeze an electron into the nucleus, its momentum would become so uncertain that it would have enormous kinetic energy, providing the force needed to escape. This uncertainty principle creates what physicists call zero-point energy, the minimum energy that a quantum system can have. Even at absolute zero temperature, electrons retain this zero-point motion, preventing them from falling into the nucleus. The Pauli exclusion principle provides additional stability. No two electrons in an atom can have identical quantum properties, so they stack up in shells around the nucleus, each occupying its own quantum state. This creates the orderly electron configurations that determine atomic properties. These quantum effects create atomic orbitals, the three-dimensional probability clouds, where electrons are likely to be found. These orbitals have beautiful mathematical shapes that reflect the wave nature of electrons. The 1s orbital is spherical. The 2p orbitals are dumbbell-shaped, and higher orbitals create increasingly complex patterns. But quantum mechanics doesn't just prevent collapse. It creates a new kind of stability. Atoms in their ground state, lowest energy configuration, are absolutely stable according to quantum mechanics. They can't lose any more energy because there's no lower energy state to transition to. They've reached the bottom of the quantum ladder and can go no further. This quantum stability is what allows chemistry to exist. Chemical bonds form when atoms share or transfer electrons, creating molecular orbitals that are stable quantum states spanning multiple atoms. The same principles that prevent atomic collapse also govern the formation of molecules, crystals, and all the complex structures that make life possible. Quantum tunneling adds another dimension to atomic stability. Electrons can tunnel through energy barriers that should be impossible to cross classically. This allows many chemical reactions to occur at reasonable rates, and is essential for processes like photosynthesis and cellular respiration. The quantum nature of atoms also explains why matter has the properties it does. The discrete energy levels create the specific heat capacities of materials, the colors of gems, the conductivity of metals, and the transparency of glass. Every material property ultimately traces back to the quantum behavior of electrons in atoms. And that brings us to the enormous energies locked within these stable quantum structures. Energies that dwarf anything available from chemical reactions. Inside every atom lies a secret that humanity discovered only recently, an almost unimaginable amount of energy, locked away in the nucleus like a genie in a bottle. This energy is so concentrated, so powerful, that a single gram of matter contains enough energy to power a city for days or level it in seconds. The story begins with Einstein's most famous equation. This simple formula reveals that mass and energy are interchangeable, that matter is actually a highly concentrated form of energy. The c in the equation represents the speed of light, about 300 million meters per second, and because this number is squared, even a tiny amount of mass corresponds to an enormous amount of energy. To put this in perspective, imagine a paperclip. If you could convert all of its mass into energy, you'd release about 18 trillion joules, enough energy to power the entire United States for several minutes. This is why nuclear reactions release millions of times more energy than chemical reactions. They tap into the mass-energy equivalence that Einstein revealed. The energy is stored in the binding energy of the nucleus, the force that holds protons and neutrons together. When nucleons bind together to form a nucleus, they give up some of their mass, converting it into binding energy. This missing mass is called the mass defect, and it represents the energy that would be required to completely disassemble the nucleus back into individual protons and neutrons. Iron 56 sits at the peak of nuclear stability, with the highest binding energy per nucleon. This means that both lighter and heavier nuclei can release energy by moving toward iron's configuration. Light nuclei can be fused together, fusion, while heavy nuclei can be split apart, fission. Both processes release energy because they create more tightly bound nuclei. Nuclear fusion is the process that powers the sun and stars. In the sun's core, hydrogen nuclei overcome their electrical repulsion and fuse together to form helium. 4 hydrogen nuclei combine to make one helium nucleus, but the helium weighs slightly less than the original hydrogen. That missing mass becomes energy, the sunlight that warms our planet and sustains all life. The conditions required for fusion are extreme, temperatures of millions of degrees and pressures millions of times greater than Earth's atmosphere. At these conditions, electrons are stripped away from nuclei, creating a plasma where naked nuclei can approach closely enough for the strong nuclear force to overcome electromagnetic repulsion. Nuclear fission, discovered in 1938 by Otto Hahn and Fritz Strassmann, involves splitting heavy nuclei into smaller fragments. When a neutron strikes a uranium-245 nucleus, it can split into two or more smaller nuclei, releasing additional neutrons and enormous amounts of energy. These released neutrons can trigger more fission reactions, creating a chain reaction that can be either controlled as in nuclear power plants, or uncontrolled, as in nuclear weapons. The energy released in fission comes from the fact that the fragments are more tightly bound than the original heavy nucleus. A uranium-235 nucleus, when split, typically produces two fragments with a combined mass slightly less than the original uranium. This mass difference becomes kinetic energy of the fragments, which is eventually converted to heat. 1 gram of uranium-235 can release about 80 trillion joules of energy, equivalent to burning about 3 tons of coal. This incredible energy density makes nuclear power both promising and dangerous. Nuclear reactors use controlled fission to generate electricity, while nuclear weapons use uncontrolled fission or fusion to release devastating amounts of energy in seconds. But nuclear energy isn't just about power plants and weapons, it's fundamental to the existence of elements themselves. Every atom heavier than hydrogen was forged in the nuclear furnaces of stars through fusion reactions. The carbon in your body, the oxygen you breathe, the iron in your blood, all were created when ancient stars converted lighter elements into heavier ones through nuclear fusion. The most massive stars end their lives in spectacular supernova explosions, where the extreme conditions allow the formation of elements heavier than iron through rapid neutron capture. These explosions scatter the newly formed elements into space, seeding the universe with the heavy elements necessary for rocky planets and life. Even the heat inside Earth comes primarily from nuclear energy. Radioactive decay of uranium, thorium, and other heavy elements in Earth's interior provides the energy that drives plate tectonics, creates our magnetic field, and keeps our planet's core molten. Without nuclear energy, Earth would be a cold, dead world. The discovery of nuclear energy also revealed the ultimate fate of the universe. Stars gradually convert hydrogen into heavier elements, but this process can't continue indefinitely. Eventually, the universe will run out of hydrogen fuel, and star formation will cease. The universe will slowly cool as existing stars burn out, leading to what cosmologists call the heat death of the universe. But nuclear energy also offers hope for humanity's future. Fusion reactors could provide clean, virtually limitless energy by recreating the processes that power the sun. Unlike fission, fusion produces no long-lived radioactive waste and cannot lead to catastrophic accidents. The fuel hydrogen from seawater is abundant and easily accessible. Nuclear medicine uses radioactive isotopes to diagnose and treat diseases. Radioisotopes can be used as tracers to follow biological processes, or as sources of radiation to destroy cancer cells. The precise control of nuclear energy at the cellular level offers new possibilities for medical treatment. The energy within atoms also reveals the deep connection between matter and energy that governs the universe. Every chemical reaction, every biological process, every thought in your brain ultimately depends on the electromagnetic energy that binds electrons to nuclei. The quantum energy levels of atoms determine the colors of light, the properties of materials, and the possibilities for chemical bonding. This atomic energy connects us to the cosmos in profound ways. The energy in your body comes from food, which gets its energy from sunlight, which comes from nuclear fusion in the sun. We are, quite literally, made of star stuff powered by star energy. And that brings us to the remarkable fact that everything in the universe, from the smallest bacteria to the largest galaxies, is built from just a few dozen types of atoms. Look around you right now. The book or screen in front of you, the air you're breathing, the chair you're sitting in, your own body, everything you can see, touch, or imagine is built from just 92 naturally occurring types of atoms. It's like discovering that every symphony ever written uses only 92 different notes, or that every painting in every museum was created with just 92 colors. This is one of the most profound simplicities in all of science. The entire universe, in all its staggering complexity and beauty, is constructed from fewer than 100 basic building blocks, and remarkably, just a handful of these elements make up the vast majority of everything we encounter. Hydrogen is the universe's favorite atom, comprising about 75% of all normal matter. It's the simplest possible atom. Just one proton and one electron, yet it's the fuel that powers stars and the raw material from which all other elements are forged. Every hydrogen atom in your body was created in the first few minutes after the Big Bang, when the universe was hot enough for protons and electrons to combine for the first time. Helium comes in second, making up about 25% of the universe's atoms. Like hydrogen, helium was created in the primordial universe, but it's chemically inert. It doesn't want to bond with other atoms. This makes helium invisible to most chemical processes, a cosmic wallflower that rarely participates in the dance of molecular formation. After hydrogen and helium, the abundance of elements drops off dramatically. The next most common elements, carbon, nitrogen, oxygen, neon, silicon, and iron, were all forged in the hearts of stars through nuclear fusion. These elements are the building blocks of rocky planets, atmospheres, and life itself. Carbon is perhaps the most remarkable element of all. With its 4 outer electrons, carbon can form 4 strong bonds with other atoms, creating an almost infinite variety of molecular structures. Carbon chains can be straight or branched, rings or networks, simple or incredibly complex. This versatility makes carbon the backbone of all known life. Every living thing on Earth is built around carbon chemistry. Your DNA, your proteins, your cell membranes, all are intricate carbon-based molecules. The carbon in your body has been recycled countless times through plants, animals, and the atmosphere. Some of your carbon atoms may have been part of a dinosaur, a tree, or a primordial ocean. Oxygen is the breath of life. Literally, it makes up about 21% of our atmosphere and is essential for the cellular processes that power complex life. Oxygen is also the most common element in Earth's crust, bound up in rocks and minerals. The oxygen you breathe was created by photosynthesis in plants and algae, which split water molecules and release oxygen as a waste product. Silicon, oxygen's chemical cousin, is the foundation of the solid Earth. Silicon dioxide quartz is one of the most common minerals on our planet, and silicon-based compounds make up most rocks and soils. Silicon's ability to form strong bonds with oxygen creates the crystalline structures that give minerals their hardness and stability. Iron is the cosmic dividing line between fusion and fission. Stars can fuse elements up to iron, but creating heavier elements requires energy input rather than release. Iron is also essential for life. It's the heart of hemoglobin molecules that carry oxygen in your blood. The iron in your blood was forged in the core of a massive star that exploded billions of years ago. The heavier elements, gold, silver, platinum, uranium, are cosmic rarities, created only in the extreme conditions of exploding stars or neutron star collisions. These elements are precious, not just economically, but literally. They represent some of the rarest events in the universe. Nuclear processes so extreme that they occur only in the most violent cosmic catastrophes. But it's not just which elements exist that's remarkable, it's how they're distributed. The human body is made primarily of just 6 elements. Oxygen, 65%, carbon 18%, hydrogen 10%, nitrogen 3%, calcium 1.5%, and phosphorus 1%. These 6 elements account for 99% of your body's atoms. Yet they create the incredible complexity of living systems. Your brain contains about 86 billion neurons, each one a complex molecular machine built from these simple atomic components. The thoughts you're having right now, the very act of reading and understanding these words, emerges from the interactions of atoms that were forged in ancient stars and assembled through billions of years of cosmic evolution. Plants demonstrate the same principle of complexity from simplicity. A towering oak tree is built primarily from carbon dioxide absorbed from the air and water absorbed from the soil. Through photosynthesis, the tree uses solar energy to combine these simple molecules into the complex carbohydrates, proteins, and lignin that make up its structure. The tree literally builds itself from thin air, using just sunlight as an energy source. The ocean, covering 71% of Earth's surface, is primarily hydrogen and oxygen in the form of water molecules. But dissolved in that water are traces of nearly every element on the periodic table. Seawater is a dilute solution of the entire periodic table, a cosmic soup containing samples of stellar nucleosynthesis spanning billions of years. Even the seemingly empty space between stars isn't truly empty. The interstellar medium contains sparse clouds of hydrogen and helium, along with traces of heavier elements blown out from dying stars. These clouds are the nurseries where new stars and planets form. recycling the elements created in previous generations of stars. The geological processes on Earth continuously recycle elements between the atmosphere, oceans, and solid crust. Carbon cycles through the atmosphere as carbon dioxide gets incorporated into living organisms and eventually returns to the atmosphere through respiration and decay. Water evaporates from the oceans, forms clouds, falls as rain, and flows back to the sea, carrying dissolved minerals and nutrients. This cosmic recycling means that the atoms in your body have incredibly ancient and diverse histories. The calcium in your bones may have been part of an ancient sea creature's shell. The iron in your blood may have been forged in a star that died before our solar system was born. The oxygen in your lungs may have been produced by a dinosaur or a fir. The universality of atomic building blocks also suggests profound possibilities. If life emerged on Earth from the interactions of carbon, hydrogen, oxygen, and nitrogen, then life might be possible anywhere in the universe where these elements exist under suitable conditions. The same atoms that make up your body exist throughout the cosmos, governed by the same physical laws and chemical principles. And that brings us to the beautiful organization of these elements, the periodic table, which reveals the hidden patterns and relationships among atomic building blocks. There's something almost magical about the periodic table hanging on classroom walls around the world like a cosmic cheat sheet. This elegant grid of elements reveals one of the most beautiful patterns in all of science, the way atomic properties repeat in predictable cycles as you add protons one by one to the nucleus. The story begins with Dmitry Mendeleev, a Russian chemist who in 1869 was struggling to organize what seemed like a chaotic collection of elements. At the time, about 60 elements were known, each with its own peculiar properties. Some were metals, some were gases, some were reactive, others were inert. There seemed to be no rhyme or reason to their behavior, but Mendeleev noticed something remarkable. When he arranged the elements by atomic weight, their properties repeated in a regular pattern. Every eighth element had similar characteristics, like musical notes repeating every octave. Lithium, sodium, and potassium all had similar properties. So did fluorine, chlorine, and bromine. The elements seemed to be singing a chemical harmony. Even more boldly, Mendeleev predicted the existence of undiscovered elements to fill gaps in his table. He described the properties these missing elements should have, based on their position in the pattern. When gallium, scandium, and germanium were later discovered, with almost exactly the properties Mendeleev had predicted, the scientific world was amazed. But Mendeleev didn't know why his periodic table worked. That understanding came only with the discovery of atomic structure and electron shells. The periodic table is actually a map of electron configurations, showing how electrons fill up shells around the nucleus as you move from element to element. The table's structure reflects the shell structure of atoms. The first row, period, contains only hydrogen and helium, because the first electron shell can hold only 2 electrons. The second row has 8 elements because the second shell can hold 8 electrons. The third row also has 8 elements for the same reason, though the third shell can actually hold more electrons. The next shell begins filling before the third shell is completely full. This shell-filling pattern creates the periodic table's characteristic shape. The tall columns on the left and right represent the SAID and p orbitals filling. The broad middle section represents the d orbitals of the transition metals. The lanthanides and actinides, usually shown separately at the bottom, represent the Fe orbital. Each column group of the periodic table represents elements with the same number of electrons in their outermost shell. This gives them similar chemical properties. Group 1 elements, lithium, sodium, potassium, all have 1 outer electron and readily give it up, making them highly reactive metals. Group 17 elements, fluorine, chlorine, bromine, all have 7 outer electrons and eagerly accept 1 more, making them reactive non-metals. The noble gases in Group 18 have complete outer electron shells, making them chemically inert. They're the aristocrats of the periodic table, aloof and unreactive, because they've achieved electronic perfection. For many years, chemists thought noble gases couldn't form compounds at all, though we now know that some can be coaxed into chemical reactions under extreme conditions. The periodic table also reveals trends in atomic properties. As you move down a column, atoms get larger because they have more electron shells. As you move across a row, atoms generally get smaller because increasing nuclear charge pulls the electrons closer, These size trends determine how elements behave in chemical reactions. Electronegativity. An atom's ability to attract electrons follows a diagonal pattern across the table. Fluorine in the upper right is the most electronegative element, greedily hoarding electrons. Francium in the lower left is the least electronegative, readily giving up electrons. This pattern creates the fundamental divide between metals and non-metals. The periodic table also predicts how elements will bond. Metals tend to lose electrons and form positive ions, while non-metals tend to gain electrons and form negative ions. When metals and non-metals combine, they form ionic compounds like salt. When non-metals combine with each other, they share electrons to form covalent compounds like water. But the periodic table holds deeper secrets. The seemingly random atomic weights that puzzled early chemists actually reflect the nuclear processes that created the elements. Elements with even numbers of protons tend to be more abundant than those with odd numbers, because even-numbered nuclei are more stable. The zigzag pattern of abundance versus atomic number tells the story of stellar nucleosynthesis. The table also reveals the limits of matter. Beyond uranium, element 92, all elements are artificially created and radioactive. These super-heavy elements exist for only fractions of a second before decaying into lighter elements. Scientists are racing to create new elements and explore the theoretical island of stability, where some super-heavy elements might be relatively long-lived. The periodic table isn't just a reference tool, it's a prediction machine. It tells us how elements will behave in chemical reactions, what types of bonds they'll form, and what properties their compounds will have. It's a roadmap for discovering new materials, designing new drugs, and understanding the fundamental chemistry of life. Modern versions of the periodic table reveal even more patterns. The electron configurations create recurring patterns in atomic radii, ionization energies, and electron affinities. These patterns help explain why carbon is perfect for forming the backbone of biological molecules, why silicon is ideal for computer chips, and why rare earth elements are essential for modern electronics. The periodic table also hints at the fundamental unity of matter. Despite their vastly different properties, all elements are variations on the same atomic theme, electrons arranged in shells around a nucleus. The diversity of the material world, from the softness of sodium to the hardness of diamond, emerges from simple differences in electron arrangement. And that brings us to the dynamic nature of atoms. The fact that they're never truly at rest, always in motion, always vibrating with thermal energy. Have you ever watched steam rise from your morning coffee? That gentle dance of vapor curling and disappearing into the air. There's something almost hypnotic about it. You're watching atoms in their most honest state, restless, eternal dancers who never learn to sit still. Temperature isn't what we think it is. It's not the number on a thermometer or the feeling of warmth on your skin. Temperature is actually the speed of tiny invisible dancers. Atoms jiggling, vibrating, spinning in their own microscopic celebration. The hotter something gets, the faster they dance. The colder it becomes, the slower their rhythm. Imagine atoms as people at a party. At a quiet gathering, everyone moves slowly, maybe swaying gently to soft music. But as the energy builds, the dancing becomes more frenzied, more chaotic. That's heat, not a thing you can touch, but a measure of how enthusiastically atoms are moving. Even in something that seems perfectly still, like the wooden table beside you, atoms are dancing. They're locked in their crystalline formations, but they're still vibrating, still moving in their tiny confined spaces. It's like a room full of people all dancing in place, unable to leave their spots but unable to stop moving either. And here's where it gets beautifully strange. At absolute zero, that theoretical temperature where everything should freeze completely, atoms would still have what scientists call zero-point energy. Even in perfect stillness, there's still a whisper of motion, a quantum flutter that refuses to be silenced. It's as if the universe itself won't allow perfect stillness. This atomic motion is what makes ice melt and water boil. It's what makes metal expand in summer heat and contract in winter cold. Every phase change, every transformation of matter, is really just atoms changing their dance style. From the rigid formation of ice crystals to the wild, free-flowing chaos of steam. It's all choreography at the atomic level. The ancient Greeks had a word for this constant motion chaos, but they weren't thinking of disorder. They were thinking of the fundamental dance that underlies all existence. Every breath you take, every heartbeat, every thought, it's all atoms in motion, following rhythms older than stars. There's something tender about the way atoms reach for each other. Like shy children on a playground, they're drawn together by invisible forces, forming friendships that can last microseconds or millennia. Chemical bonding isn't really about chemicals at all. It's about loneliness and completion. Every atom carries around its own electrical personality, and most of them feel incomplete on their own. They're like puzzle pieces searching for their perfect fit. Take sodium and chlorine. Table salt. Sodium is like that friend who's always giving things away, generous to a fault. It happily gives up an electron, becoming positively charged. Chlorine is the opposite. It's always collecting things, hoarding electrons like a cosmic collector. When they meet, it's perfect. Sodium offers its extra electron, chlorine accepts it gratefully, and suddenly they're both content, locked together in an ionic embrace. But there's another kind of bonding, more intimate and complex. Covalent bonds are like atoms deciding to share their most precious possessions, their electrons. Imagine two people, so close they share everything, their time, their space, even their thoughts. That's what happens when atoms form covalent bonds. They overlap their electron clouds, creating shared spaces where electrons can roam freely between both atomic nuclei. Water is the perfect example of this atomic partnership. Each water molecule is like a tiny family, one oxygen atom, holding hands with two hydrogen atoms. The oxygen is larger, more dominant, pulling the shared electrons closer to itself. This creates a slight imbalance, making water molecules slightly positive on one end and slightly negative on the other. It's this personality quirk that makes water so good at dissolving things, so essential for life. Some atoms are serial bonders, carbon being the most social of all. Carbon atoms can link up in chains, rings, complex three-dimensional structures. They're like the extroverts of the atomic world, always ready to form new connections. This is why carbon is the backbone of all life. It's literally the atom that knows how to make friends. And then there are the noble gases, helium, neon, argon, the loners of the atomic world. They're already complete, already satisfied with their electron arrangements. They rarely bond with anything, preferring to drift alone through the universe like cosmic hermits. There's something poetic about their independence, their refusal to be changed by others. Chemical reactions are really just atoms changing partners, breaking old bonds and forming new ones. Like a cosmic square dance, atoms swap partners, creating new molecules with completely different personalities. Hydrogen and oxygen become water. Carbon and oxygen become carbon dioxide. The same atoms but with entirely different stories to tell. The universe is constantly rewriting itself through these atomic partnerships. Close your eyes and imagine throwing a ball at a wall. In our everyday world, that ball bounces back. It can't pass through solid matter. But in the quantum world where electrons live, the impossible happens regularly. Electrons can walk through walls like ghosts, appearing on the other side without ever crossing the barrier in between. This is quantum tunneling. And it's not science fiction, it's the everyday reality of subatomic particles. Electrons don't follow the rules we learned in school. They don't orbit the nucleus like planets around the sun. Instead, they exist in fuzzy probability clouds, regions where they might be found if we go looking for them. Think of an electron as being like a shy cat that only appears when you're not looking directly at it. The moment you try to pin down exactly where it is, it becomes uncertain where it's going. The more precisely you know its location, the less you can know about its momentum. This isn't a limitation of our measuring tools, it's a fundamental property of reality itself. Werner Heisenberg discovered this uncertainty principle in the 1920s, and it shattered our comfortable notions of a predictable universe. At the quantum level, particles don't have definite positions or velocities. They exist in what scientists call superposition, multiple states at once, like a coin that simultaneously heads and tails until someone looks at it. An electron in an atom doesn't have a specific orbit. Instead, it has an orbital, a three-dimensional region where it's likely to be found. These orbitals have beautiful names. S orbitals are spherical clouds, p orbitals are dumbbell-shaped, d orbitals are even more complex, like flowers blooming in impossible dimensions. But here's where it gets truly strange. Electrons can tunnel through energy barriers that should be impossible to cross. Imagine you're hiking and you come to a mountain too high to climb over. In the quantum world, you could just walk through the mountain and emerge on the other side. This isn't magic. It's the fundamental weirdness of quantum mechanics. This quantum tunneling is happening in your body right now. The nuclear fusion in the sun that provides the energy for all life on Earth relies on quantum tunneling. The protons in the sun's core don't have enough energy to overcome their electrical repulsion, but they tunnel through the energy barrier anyway, allowing fusion to occur. Even the electronics in your phone depend on quantum tunneling. The tiny transistors that make computation possible work because electrons can tunnel through barriers that would stop them in the classical world. Schrödinger tried to illustrate this quantum weirdness with his famous thought experiment about a cat that's simultaneously alive and dead. He wasn't being silly, he was pointing out how strange our universe becomes when we look closely enough. The quantum world operates on possibilities and probabilities, not certainties. And perhaps most mysterious of all, the quantum world seems to know when we're watching. The act of observation changes the behavior of particles. It's as if the universe is playing an elaborate game of hide and seek, revealing its secrets only when we're not looking directly at them. There's a moment in human history when we learned to touch the fire that burns inside stars. It happened in a squash court beneath the Ulyss of Chicago in 1942, when Enrico Fermi and his team achieved the first controlled nuclear chain reaction. They had learned to split the atom, to release the energy that had been locked away for billions of years. The story begins with a discovery that seemed almost too simple to be true. In 1938, Otto Hahn and Fritz Strassmann were bombarding uranium with neutrons, expecting to create heavier elements. Instead, they found something impossible: barium, an element much lighter than uranium. It was as if they had tried to crack a walnut and found an apple inside. Liz Meitner, working with her nephew Otto Frisch, realized what had happened. The uranium nucleus wasn't just absorbing the neutron, it was splitting in half, like a droplet of water dividing into two smaller droplets. They called it nuclear fission, and they calculated that this splitting released enormous amounts of energy. Einstein's famous equation E=mc² had predicted this possibility. A tiny amount of mass, smaller than a grain of sand, could be converted into energy equivalent to tons of dynamite. The atom, which had once seemed like the smallest, most stable thing in the universe, was revealed to be a vast storehouse of energy. But fission wasn't just a laboratory curiosity. Each time a uranium nucleus split, it released not just energy but also more neutrons. These neutrons could strike other uranium nuclei, causing them to split and release even more neutrons. It was like a cosmic chain reaction, each split leading to more splits, energy multiplying exponentially. The mathematics were both beautiful and terrifying. Under the right conditions, this chain reaction could be controlled, providing a new source of energy. Under the wrong conditions, it could create an explosion more powerful than anything humans had ever imagined. The nuclear age began with hope and ended with horror. The same scientific principles that could power cities were used to destroy them. Hiroshima and Nagasaki became terrible proof of the energy hidden inside atoms. In milliseconds, the binding energy that held atomic nuclei together was released, creating temperatures hotter than the surface of the sun. Yet nuclear fission also opened doors to healing. Radioactive isotopes created in reactors became powerful tools for medicine, helping doctors peer inside the human body and treat diseases. The same process that could destroy could also save lives. The atom, once thought to be indivisible, revealed itself to be a complex system of incredible forces held in delicate balance. When that balance is disturbed, the results can be either miraculous or catastrophic. It depends entirely on human wisdom and restraint. We had learned to split the atom, but in doing so we had also split our own future into two possibilities. Right now, as you breathe, you're inhaling atoms that were once part of dinosaurs, ancient trees, and distant stars. Your body is a temporary gathering place for atoms that have been wandering the universe for billions of years, and they'll continue their journey long after you're gone. You are made of about 7 octillion atoms, that's 7 followed by 27 zeros. It's a number so large it's almost meaningless, like trying to count all the grains of sand on every beach on Earth. But what's even more remarkable is what kinds of atoms you're made of. Your body is mostly hydrogen and oxygen, the ingredients of water. About 60% of your body weight is water, which means you're mostly empty space held together by electromagnetic forces. The hydrogen atoms in your water were forged in the first few minutes after the Big Bang, making them some of the oldest things in the universe. But you're not just water, you're carbon. The backbone of every protein, every strand of DNA, every cell membrane. These carbon atoms were cooked in the hearts of dying stars, compressed under unimaginable pressure and temperature, until they became the building blocks of life. The carbon atom that's part of a protein in your muscle might have once been part of a leaf, or a piece of coal, or even another person who lived centuries ago. Your bones are made largely of calcium and phosphorus, elements that were scattered across the galaxy by supernovas billions of years ago. The iron in your blood, the metal that carries oxygen from your lungs to your cells, was forged in the core of a star that exploded before our solar system even existed. Every atom in your body is an immigrant from somewhere else in the universe. None of them were born here on Earth. They've all traveled unimaginable distances and survived cosmic catastrophes to end up, temporarily, as part of you. And here's something that might change how you think about yourself. You replace most of the atoms in your body every few years. The carbon atoms in your muscles are replaced every few months. The atoms in your liver are replaced every few weeks. Even the atoms in your brain, the physical substrate of your thoughts and memories, are constantly being swapped out for new ones. This means that, atomically speaking, you're not the same person you were 7 years ago. You're like a river that maintains its shape, while the water constantly flows through it. Your identity, your memories, your personality, they all persist, even as your physical atoms come and go. The nitrogen in your DNA, the sodium in your nerves, the magnesium in your chlorophyll. Wait, you don't have chlorophyll, but the plants you eat do, and their atoms become your atoms. We're all part of the same cosmic recycling program, sharing atoms across species and across time. Some of the atoms in your body might have been part of Napoleon, or Shakespeare, or a T-Rex. Statistics suggest that you probably contain atoms that were once part of every person who ever lived. We're all connected at the atomic level, part of an endless circulation of matter through the universe. You are made of star stuff, but you're not just a collection of atoms. You're a pattern, a temporary arrangement of matter that has learned to think about itself. Every atom in your body except hydrogen has a stellar birth certificate. They were forged in the nuclear furnaces of stars, created in conditions so extreme that they can barely be imagined. The calcium in your bones, the iron in your blood, the oxygen you breathe, they all came from stars that died billions of years ago. In the beginning there was almost nothing. The early universe was mostly hydrogen and helium, the two simplest elements. But hydrogen had a gift. It could gather itself into vast clouds, and these clouds could collapse under their own gravity until they became hot enough to ignite. The first stars were born. Inside these stellar furnaces, something magical happened. The temperature and pressure were so intense that hydrogen nuclei could overcome their natural repulsion and fuse together, creating helium. This nuclear fusion released enormous amounts of energy, enough to make stars shine for millions or billions of years. But stars are not content to make just helium. As they age, they begin fusing helium into carbon, carbon into oxygen, oxygen into neon. Layer by layer, like an onion, stars build up heavier and heavier elements in their cores: silicon, sulfur, argon, calcium. Each fusion reaction creates something new, something that had never existed before in the universe. The most massive stars become cosmic alchemists, transforming simple hydrogen into the entire periodic table. They create sodium and aluminum, phosphorus and chlorine, potassium and iron. They're like universal factories, manufacturing the raw materials needed for planets and life. But this process has a limit. Iron is the end of the line. When a star tries to fuse iron, it doesn't release energy, it absorbs it. The star's core suddenly collapses, and the outer layers explode outward in a supernova, one of the most violent events in the universe. This explosion is more than just spectacular, it's generous. All the elements the star has created over millions of years are scattered across space, seeding the galaxy with the building blocks of complexity. The shockwave from the supernova also creates even heavier elements: gold, silver, uranium, through rapid neutron capture. These stellar ashes drift through space for millions of years, eventually collecting into new clouds of gas and dust. When these clouds collapse to form new stars, they also create planets, rocky worlds made from the recycled atoms of previous stellar generations. Our Sun is one of these second-generation stars, formed from a cloud that contained the ashes of earlier stars. The Earth itself is made from stellar debris, Every grain of sand, every drop of water, every living thing built from atoms that once burned in the heart of a star. Carl Sagan said it best, "We are made of star stuff." But it's more than just poetry, it's literally true. The atoms in your body have traveled across the galaxy, survived the death of stars, and somehow arranged themselves into the complex pattern that is you. When you look up at the night sky, you're not just seeing distant lights, you're seeing your ancestors, the stellar furnaces that created the atoms you're made of. You're part of an unbroken chain of cosmic evolution, a story that began with the simplest elements and led, somehow, to consciousness. The elements in your body are not just old, they're ancient beyond comprehension. They've been recycled through multiple generations of stars, through supernovas and planetary formation, through the slow alchemy of geology and biology. You are the universe looking back at itself. Some atoms are impatient. They can't sit still, can't maintain their form, can't resist the urge to change into something else. These are the radioactive elements, and they keep perfect time, not with clocks or calendars, but with the fundamental rhythm of nuclear decay. Radioactivity isn't a malfunction or a mistake. It's the universe's way of editing itself, of transforming unstable atoms into more stable forms. Some atomic nuclei are simply too heavy, too energetic, too unbalanced to maintain their structure forever. They're like houses built on shaky foundations. Eventually, something has to give. When an unstable nucleus decays, it releases energy and particles, transforming into a different element entirely. Uranium slowly becomes thorium, then protactinium, then another isotope of uranium, working its way down a long chain of decay until it finally becomes lead, stable, content, at peace. This process follows its own inexorable schedule. Every radioactive isotope has what scientists call a half-life, the time it takes for half of a sample to decay. Some isotopes have half-lives measured in fractions of seconds, others take billions of years, but each follows its own precise temporal rhythm. Carbon-14 has a half-life of 5,730 years, making it perfect for dating archaeological specimens. When living things die, they stop absorbing new carbon-14 from the atmosphere. The carbon-14 already in their bodies begins its slow decay, like a biological clock that starts ticking the moment life ends. Uranium-2038 has a half-life of 4.5 billion years, roughly the age of the Earth. This means that half of the uranium-2038 that existed when our planet formed is still here, still slowly decaying. The other half has transformed into lead, grain by grain, atom by atom, over geological time. Some radioactive elements are so short-lived that they barely exist. Technetium-99, used in medical imaging, has a half-life of just 6 hours. By the time it travels from the nuclear reactor where it's made to the hospital where it's used, much of it has already decayed. It's like a message written in disappearing ink. But radioactive decay isn't just about time. It's about probability. You can't predict when any individual atom will decay. It might happen in the next second, or it might wait billions of years. But in a large sample, the statistical average is absolutely predictable. It's like flipping coins. You can't predict any individual flip, but you can predict the pattern over many flips. This quantum uncertainty extends to the very heart of matter. Each atomic nucleus is like a tiny casino, playing games of chance with the fundamental forces of nature. Most of the time, the strong nuclear force wins, holding protons and neutrons together, but occasionally, randomly, the electromagnetic force wins, and the nucleus splits apart. Radioactive decay has become humanity's most precise clock. We use it to date rocks, fossils, and archaeological artifacts. We use it to understand the age of the Earth, the solar system, and even the universe itself. Atoms that were unstable when they formed billions of years ago are still faithfully ticking away, measuring time on scales that dwarf human experience. The atoms in your body are mostly stable, but not perfectly so. You contain tiny amounts of radioactive elements. Carbon-14, potassium-40, even traces of uranium. Right now, about 15 atoms in your body are decaying every second. You are, quite literally, a very mild radioactive source. But don't worry, this radioactive decay is part of the natural background of existence. Life evolved in a radioactive world, and we've learnt to live with this constant, gentle transformation. We are not separate from the atomic world, We are part of its eternal dance through time. Here's a question that might keep you awake at night. How do unconscious atoms combine to create conscious thought? You are made entirely of particles that individually have no awareness, no intention, no experience, yet somehow, when arranged in the right pattern, they begin to think about themselves. Your brain contains roughly 86 billion neurons, each one a complex arrangement of carbon, hydrogen, oxygen, and other atoms. These atoms follow the same physical laws as atoms everywhere else in the universe. They're not special, they're not conscious, they're just matter. But when these atoms arrange themselves into the intricate networks of your brain, something extraordinary happens. Patterns emerge. Information flows. Consciousness awakens. It's like a symphony arising from individual musicians who don't know they're part of a larger performance. Each neuron is essentially a biological computer, processing electrical and chemical signals. But a neuron is just atoms arranged in a particular way. The sodium and potassium atoms that flow across neural membranes don't know they're participating in thought. They're just following the laws of physics, moving from high concentration to low concentration, like water flowing downhill. Yet somehow, this flow of mindless atoms creates the experience of being you, your memories, your emotions, your sense of self. All of it emerges from the coordinated dance of particles that have no memory, no emotions, no sense of self. This is perhaps the deepest mystery in science. We can explain how atoms bond, how they move, how they interact. We can trace the electrical signals in your brain, map the neural networks that correspond to different thoughts and experiences. But we can't explain why any of this should feel like anything at all. Some philosophers argue that consciousness is an illusion, a story we tell ourselves about the complex information processing in our brains. Others suggest that consciousness is a fundamental property of matter, that even individual atoms have some primitive form of experience that adds up to our rich inner lives. But here's what we do know. The atoms in your brain are constantly being replaced. The carbon atoms in your neurons are swapped out every few weeks. The calcium atoms in your synapses are replaced regularly. Yet your consciousness, your sense of being you, persists through all these changes. This suggests that consciousness isn't located in any particular atom or even any particular set of atoms. It's a pattern, a process, a dynamic organization of matter that maintains its identity even as its components change. You are like a flame, not a thing, but a process that maintains its form while its substance flows through it. The atoms in your brain right now might have been part of other brains, other minds, other thought. The carbon atom participating in your memory of childhood might have once been part of a tree, or a dinosaur, or another person's dream. Matter is recycled, but the patterns it creates, the thoughts, the experiences, the moments of awareness, are unique and irreplaceable. We are the universe, becoming aware of itself through the arrangement of its own atoms. We are matter organized in such a way that it can contemplate its own existence. We are the cosmos, thinking about itself, one thought at a time. The atoms don't think, but somehow, when they come together in the right way, thinking emerges. It's not magic, it's something stranger and more wonderful than magic. It's the mystery of consciousness arising from the dance of unconscious particles. Here's a thought that might make you feel a little dizzy. The atoms you've been learning about might not exist the way you think they do. In fact, they might not exist at all in any way we can meaningfully call real. When you picture an atom, you probably imagine a tiny solar system, electrons orbiting a nucleus like planets around the sun. But this image, comfortable as it is completely wrong. Atoms don't look like anything. They don't have a shape, a color, or a definite size. They exist in a realm where our everyday concepts of reality break down. The problem began when scientists started looking more closely at atoms. The more precisely they tried to measure atomic properties, the more elusive atoms became. Werner Heisenberg discovered that you can't simultaneously know both the position and momentum of a particle. The more accurately you measure one, the less accurately you can know the other. This isn't just a practical limitation, it's a fundamental feature of reality. Atoms don't have definite properties until we measure them. Before measurement, an electron doesn't have a specific location or velocity. It exists in a fuzzy cloud of possibilities, what physicists call a superposition of state. But here's where it gets really strange. The act of measurement doesn't just reveal what was already there, it actually creates the reality it measures. When you observe an electron, you force it to choose a specific position or momentum. Before observation, these properties didn't exist in any meaningful sense. This is the famous measurement problem in quantum mechanics. Reality seems to depend on observation. But what counts as an observation? Does it require a conscious observer? Does the universe exist differently when no one is looking? Some interpretations of quantum mechanics suggest that atoms exist in multiple states simultaneously, until observed. Others propose that there are countless parallel universes, each representing different possible outcomes of quantum events. Still others argue that atoms are just mathematical abstractions, useful for making predictions but not corresponding to anything physically real. The Copenhagen interpretation developed by Niels Bohr and others suggests that asking whether atoms are real is the wrong question. Atoms are models, tools for understanding and predicting the behavior of matter. They're useful fictions that help us make sense of experimental results. But if atoms aren't real in the way we imagine, what are we made of? What is the physical world? These questions lead to the edge of human understanding, where science meets philosophy, and both begin to break down. Some physicists now think of atoms not as tiny objects but as patterns of information, mathematical structures that describe how matter behaves. The universe might be less like a machine made of parts, and more like a vast, self-organizing pattern of information processing. This doesn't mean atoms are just mathematics. Mathematics, after all, is remarkably good at describing and predicting the behavior of matter. The equations of quantum mechanics are among the most successful theories in science, making predictions accurate to more than 10 decimal places. But it does suggest that reality is far stranger and more subtle than our everyday experience suggests. We are not made of tiny, solid building blocks. We are patterns of possibility, dynamic organizations of information and energy that maintain their structure while their components flow through them. The atoms that make up your body are real in the sense that they have measurable effects on the world, but they're not real in the sense of being tiny, solid objects with definite properties. There's something stranger, quantum possibilities that become definite only when they interact with the world around them. We are made of mystery, held together by forces we don't fully understand, in a universe that becomes real only when we look at it. The discovery of atomic structure didn't just change science, it changed everything. It reshaped our understanding of matter, energy, time, and space. It gave us new powers and new responsibilities. It revealed the universe to be far stranger and more wonderful than anyone had imagined. Before atoms, the world seemed solid, predictable, mechanical. Matter was matter, energy was energy, and time flowed steadily forward. But atomic physics revealed that matter and energy are interchangeable, that time is relative, that the very act of observation changes reality. The practical consequences were enormous. Understanding atomic structure led to the development of semiconductors, which gave us computers, smartphones, and the internet. It led to medical imaging technologies that can see inside the human body without surgery. It led to nuclear power, which can light cities or destroy them. But perhaps the most profound impact was philosophical. The atomic view of reality challenged our basic assumptions about the nature of existence. If we are made of atoms, and atoms are mostly empty space, then we are mostly empty space. If atomic behavior is fundamentally probabilistic, then the universe is not a clockwork machine, but a cosmic casino. The atomic age began with hope and wonder. Scientists like Marie Curie, Ernest Rutherford, and Niels Bohr were driven by pure curiosity about the fundamental nature of matter. They weren't trying to build weapons or power plants. They were trying to understand how the world works. But scientific knowledge is morally neutral. The same understanding that led to life-saving medical technologies also led to weapons of unprecedented destructive power. The same nuclear physics that could provide clean energy could also contaminate the environment for thousands of years. Atomic science forced humanity to confront difficult questions about knowledge and responsibility. Just because we can split the atom, should we? Just because we can split the atom, should we? We can now manipulate individual atoms, creating new materials with precisely engineered properties. We can use atomic-scale processes to store vast amounts of information in tiny spaces. We can even use quantum effects to create new forms of computation that were impossible before. But each new capability brings new challenges. Nanotechnology promises revolutionary advances in medicine, energy and materials science, but it also raises concerns about unknown risks and unintended consequences. Quantum computing could solve problems that are currently intractable, but it could also break the encryption systems that protect our digital privacy. The atomic legacy is complex and ongoing. We are still learning to live with the knowledge that we are made of atoms, that reality is quantum, but matter and energy are interchangeable. We are still grappling with the ethical implications of atomic power and atomic weapons. But there's also something beautiful about the atomic view of reality. It reveals the deep connections between all things, the way we are literally made of star stuff, the way consciousness emerges from the dance of unconscious particles. It shows us that the universe is not a collection of separate objects, but a unified field of matter and energy, constantly transforming itself into new patterns of organization. The atom taught us that we are not separate from the universe. We are the universe, temporarily organized into the complex patterns that allow it to think about itself. We are matter that has learned to contemplate its own existence. Atoms that have arranged themselves into the most complex structures known to science. Conscious minds capable of wonder, curiosity and love. The atomic age is not just a period in human history. It's a stage in the universe's long journey towards self-understanding. So here we are, at the end of our journey through the atomic world, and the question remains, what is an atom really? We started with the idea that atoms are the smallest pieces of matter, indivisible building blocks of reality. We discovered that atoms are mostly empty space, held together by forces we can barely comprehend. We learned that they're not really particles at all, but fuzzy clouds of possibility that become definite only when observed. We found that atoms are ancient wanderers, forged in the hearts of dying stars, recycled through countless forms before temporarily becoming part of you. We discovered that they're constantly in motion, dancing to rhythms older than the Earth, following probability patterns that make the universe fundamentally uncertain. We learned that atoms can transform themselves, changing from one element to another through radioactive decay, keeping perfect time across geological ages. We found that they can tunnel through barriers, exist in multiple states simultaneously, and behave in ways that defy common sense. We discovered that atoms are not just matter, they're information pattern process. They're the universe's way of organizing itself into ever more complex forms, eventually creating structures so sophisticated that they can contemplate their own existence. But after all this learning, the atom remains mysterious. It's simultaneously the most real thing we know, the fundamental constituent of everything, and the most elusive, existing only as mathematical probabilities until observed. It's both ancient and eternal, both simple and impossibly complex. Perhaps the atom is best understood, not as a thing, but as a question. It's the universe asking itself, what am I? How do I work? What am I capable of becoming? Every atom is a tiny experiment in existence, a test of what's possible when matter organizes itself. You are made of these questions, billions and billions of them, all asking themselves what it means to exist. Your consciousness is the universe's way of trying to understand itself, one thought at a time. Your wonder about atoms is atoms wondering about themselves. The atom is not just a scientific concept. It's a bridge between the physical and the metaphysical, between the world of matter and the world of meaning. It's where science meets philosophy, where knowledge meets mystery, where the very small reveals truths about the very large. In the end, the atom is exactly what it has always been, indivisible, not because it cannot be split, but because it cannot be separated from the rest of existence. Every atom is connected to every other atom, through the forces that bind them, the history they share, the future they're creating together. The atom is the universe's signature, written in the language of quantum mechanics and nuclear physics. It's the cosmos saying, I am here, I am real. I am becoming something more than I was. And you are the atom's way of knowing itself. You are matter that has learned to think, energy that has learned to love, information that has learned to dream. You are the universe becoming conscious of its own atomic nature. What is an atom really? It's the question that created you, the mystery that sustains you, the wonder that makes you human. It's the smallest thing that contains everything, the simplest thing that enables all complexity, the most ordinary thing that makes extraordinary things possible. The atom is you, questioning yourself. It's the universe, knowing itself. It's the eternal dance of matter and energy. playing out its infinite possibilities in the theater of space and time. And that, perhaps, is answer enough. For now, the end is just another beginning, and the atom's story continues in every breath you take, every thought you think, every moment you exist. Have you ever noticed how everything has its own sound? The hum of your refrigerator, the whisper of wind through leaves, the deep rumble of thunder. All of these sounds are really atoms talking to each other, vibrating in patterns that create the symphony of existence. Every atom has its own natural frequency, its own musical note. When atoms vibrate, they create waves in the air around them, pressure waves that travel to your ears and become sound. The faster the vibration, the higher the pitch, the slower the vibration, the deeper the tone. But atoms don't just make sound, they respond to it. Play a pure tone at exactly the right frequency, and you can make specific atoms dance. This is how microwave ovens work. They play a frequency that water molecules love to dance to, causing them to vibrate so enthusiastically that they heat up your food. Scientists have learned to listen to atoms with incredible precision. They can detect the unique frequency signature of each element, like a cosmic fingerprint made of sound. This is how we know what distant stars are made of. We listen to the light they emit, which carries the musical signatures of their atoms. Even the atoms in your body are constantly humming, vibrating at frequencies too low for your ears to detect. Your bones resonate at their own frequency, different from your muscles, different from your blood. You are a walking orchestra of atomic music, playing a song that's uniquely yours. The universe itself might be musical at the deepest level. Some theories suggest that the fundamental particles, the building blocks of atoms, are actually tiny vibrating strings, each playing its own note in the cosmic symphony. If this is true, then reality itself is made of music, and we are all part of an enormous, ever-changing composition. There's something deeply peaceful about this idea, that at the atomic level, existence is not chaos but harmony. Not noise but music. Every atom in your body is contributing to this grand performance, playing its part in the eternal song of being. This might sound strange, but atoms know about love. Not the romantic kind, of course. Atoms don't write poetry or give flowers, but they do form bonds, and these bonds are driven by something that looks remarkably like affection. When atoms come together to form molecules, they're not just randomly bumping into each other, they're actively seeking out partners that complement them, that make them feel complete. A hydrogen atom and an oxygen atom don't just accidentally become water, they're drawn to each other by forces that are fundamentally attractive. This atomic attraction follows patterns that mirror human relationships. Some atoms are generous, always ready to share their electrons. Others are possessive, hoarding electrons and rarely letting them go. Some form brief, passionate bonds that burn hot and break quickly. Others settle into stable, long-term relationships that can last for billions of years. The strongest bonds form between atoms that have what each other needs. It's like two people who complement each other perfectly, one strength balancing the other's weaknesses, creating something more beautiful together than either could be alone. But atoms can also be jealous. When a more attractive atom comes along, bonds can break and reform. Chemical reactions are often just atoms switching partners, leaving their old relationships for new ones that promise greater stability or energy. Some atoms are serial monogamists, forming one strong bond at a time. Others are polygamists, happily bonding with multiple partners simultaneously. Carbon is particularly social, able to form 4 bonds at once, creating complex molecular families. And then there are the noble gases, the loners of the atomic world. They're complete unto themselves, rarely forming bonds with anyone. They drift through the universe in splendid isolation, like cosmic bachelors who've decided they're better off alone. The love between atoms is not emotional, it's energetic. Atoms bond because it lowers their energy, makes them more stable, more content. In a way, this is not so different from human love. We're drawn to people who make us feel more complete, more at peace, more ourselves. The atoms in your body are constantly forming and breaking bonds, but most of them are in committed relationships. The carbon atoms in your DNA are bonded to other atoms in precise patterns that have remained stable for decades. They're like an old married couple, so comfortable together that they've forgotten how to be apart. Even the atoms that make up your thoughts are bound together by something like love, the electromagnetic force that holds electrons to nuclei, that allows atoms to share their most precious possessions with each other. Every thought you think is made possible by billions of tiny acts of atomic devotion. Love might be the most fundamental force in the universe, not just the emotional experience we humans treasure, but the basic attractive force that draws matter together, that creates complexity from simplicity, that makes the universe more than just a collection of isolated particles. We are made of atoms that have chosen to love each other, at least for a while. We are the temporary result of countless tiny acts of atomic affection. We are love, made manifest in the dance of matter and energy. Atoms remember everything, not in the way you remember your first kiss or your grandmother's voice, but in their own quantum way. Every interaction leaves a trace. Every collision changes them slightly. Every moment of their existence is recorded in the subtle alterations of their structure. The atoms in your body carry memories older than the Earth. The carbon atoms in your cells remember the hearts of ancient stars where they were forged. The hydrogen atoms in your water remember the first moments after the Big Bang, when the universe was hot and dense and full of possibility. But atoms also carry more recent memories. The calcium atoms in your bones remember the moment they were absorbed from the food you ate. The iron atoms in your blood remember the day they were assembled in your bone marrow. Every atom in your body carries the story of how it became part of you. This atomic memory is not conscious, but it's precise. Scientists can read the history of atoms by studying their isotopic signatures, the subtle variations in their nuclear composition that tell the story of where they've been and what they've experienced. The atoms in tree rings remember the weather patterns of decades past. The atoms in ice cores remember the composition of ancient atmospheres. The atoms in rocks remember the conditions when they were formed, preserving information about the Earth's history in their crystal structures. Even the atoms in your brain carry memories in their patterns of connection. The neural networks that store your memories are made of atoms arranged in specific ways, their bonds encoding the information that makes you who you are. Your memories are literally built from atomic memories. But here's something remarkable. The atoms that store your memories are not the same atoms that were there when the memories were first formed. The physical substrate of your memories is constantly being renewed, yet the memories themselves persist. It's as if the atoms are teaching their replacements what to remember. This suggests that memory is not located in matter, but in pattern, not in the atoms themselves but in the relationships between them. Your memories are like songs that can be played on different instruments. The melody persists even when the musicians change. The universe itself might have a memory, encoded in the quantum structure of empty space. Some theories suggest that every event leaves a permanent record in the fabric of spacetime, that nothing is ever truly lost or forgotten. We are made of atoms that remember, and we are patterns that persist across the flow of atomic memory. We are the universe's way of creating memories that can remember themselves, matter that has learned to be nostalgic about its own past. The atoms in your body will outlive you, carrying forward the memory of having been briefly organized into the pattern that was you. In a sense, you will be remembered by your atoms long after your consciousness has faded, a ghost in the machine of matter itself. Atoms love to play. They don't have recess or playgrounds, but they have their own forms of entertainment. Games of chance, probability, and quantum hide-and-seek that would make any casino jealous. The fundamental game atoms play is called quantum superposition. It's like being in multiple places at once, playing all possible games simultaneously until someone looks to see which game you're actually playing. An electron can be spinning clockwise and counterclockwise at the same time, at least until you measure it and force it to choose. Atoms also play the ultimate game of telephone. When two atoms become entangled, quantumly connected, they can instantly share information across any distance. Change the state of one atom, and its entangled partner immediately knows about it, no matter how far apart they are. Einstein called this spooky action at a distance, but atoms think it's just good communication. The electrons in atoms play a complex game of musical chairs. They occupy different energy levels, or orbitals, and they're constantly moving between them. When an electron jumps from a higher energy level to a lower one, it releases a photon of light. This is how atoms create the colors we see. They're literally playing with light. But atoms don't just play by themselves. They love party games, especially the one called chemical bonding. It's like a cosmic square dance, where atoms swap partners, share electrons, and create new molecules. Some atoms are wallflowers, preferring to stay on the sidelines. Others are social butterflies, ready to bond with anyone who will have them. The most elaborate atomic game is called life. It's an incredibly complex game where atoms organize themselves into self-replicating patterns, creating players that can play games of their own. You are the result of this game, a temporary pattern of atoms that has learned to play chess, write poetry, and contemplate the nature of existence. Atoms even play with time. Radioactive atoms play a game of cosmic roulette, randomly deciding when to decay. You can't predict when any individual atom will transform, but the overall pattern is perfectly predictable. It's like a casino where the house always wins, but individual players can get lucky. The game of nuclear fusion is perhaps the most spectacular. Atoms overcome their natural repulsion to merge with each other, creating heavier elements and releasing enormous amounts of energy. It's like a cosmic contact sport, played at temperatures of millions of degrees. But the most beautiful atomic game might be the one called consciousness. Somehow atoms have learned to play a game so sophisticated that they can contemplate their own existence. They've organized themselves into patterns that can think, feel, wonder, and love. They've created players that can appreciate the beauty of the game itself. We are atoms at play, engaged in the most complex game ever invented. We are matter that has learned to play games with itself, to create rules and break them, to find joy in the simple act of existing. We are the universe's way of playing with its own possibilities. If you could shrink down to the size of an atom, you'd find yourself in a world of perpetual motion, where everything is always dancing. There are no still moments in the atomic world, no quiet corners where matter can rest. Everything is rhythm, everything is movement, everything is dance. The nucleus dances at the center, a tight choreography of protons and neutrons spinning and vibrating in patterns held together by the strong nuclear force. It's like a cosmic ballet, with particles moving in perfect synchronization, each one aware of all the others. Around this nuclear dance floor, electrons perform their own interpretive dance. They don't orbit like planets, they exist in probability clouds, regions where they might be found if you look for them, but they're not really there until you look. They're like dancers who exist only in the moment of movement, who become real only when observed. When atoms come together to form molecules, they create ensemble dances of incredible complexity. The water molecule is a simple trio, 2 hydrogen atoms and 1 oxygen atom, performing a gentle waltz. But proteins are like vast dance companies, with thousands of atoms all moving in coordinated patterns that create the choreography of life. The temperature of matter is really just the speed of the atomic dance. In ice, atoms move slowly, locked in rigid formations like dancers in a formal minuet. In liquid water they move more freely, like dancers at a casual party. In steam they move with wild abandon, like dancers at a rave. But the most beautiful atomic dance happens when atoms bond with each other. It's like a cosmic courtship dance where atoms approach each other cautiously, test their compatibility, and either form a lasting partnership or part ways to find other dance partners. Light itself is part of the atomic dance. When electrons jump between energy levels, they emit photons, particles of light that are really just waves of electromagnetic energy. Every color you see is the result of atomic dance moves, electrons leaping and spinning and creating the visual symphony of existence. The dance of atoms is what makes chemistry possible. Chemical reactions are really just choreographed exchanges where atoms change partners, form new bonds, and create new molecular dance companies. It's like a cosmic mixer where everyone is constantly meeting new partners and trying new dance styles. Even the atoms in your body are dancing right now. The hemoglobin in your blood is performing a complex dance as it picks up oxygen in your lungs and delivers it to your cells. The enzymes in your metabolism are dancing as they catalyze the chemical reactions that keep you alive. Your thoughts are atomic dances too. The neurons in your brain are conducting elaborate choreographies of sodium and potassium ions, creating the electrical patterns that become your consciousness. Every thought you think is a dance of atoms, a pattern of movement that creates the experience of being you. We are not just made of atoms, we are atomic dances, temporary patterns of movement that maintain their identity while their components flow through them. We are the universe learning to dance with itself, matter that has become so skilled at movement that it can contemplate its own choreography. The dance never stops. Long after you're gone, your atoms will continue dancing, finding new partners, creating new patterns, participating in the eternal choreography of existence. We are brief movements in an endless dance, temporary steps in the universe's eternal waltz with itself.